We'll wait for 1 more minute for others to join. If no one else joins, then we'll start. Okay, I think we should start now. So, welcome to the week 6 of problem solving session of heat transfer.
And happy Teachers Day.
Thank you. Okay, so just 1 sec. Have all of you enjoyed on the Teachers' Day celebration?
Likewise.
Nice. Okay. So let us proceed with today's session. First, we will start with the previous days. Great. Okay. So we'll discuss previous days question. Two were left, right? So for the 13 number question that was done on previous day, second part was left to be done. That is for the 1.5 meter side. So what is said? It was said that there is a surface the local atmospheric pressure in Denver was given as 83.4 kilopascal, and here at this pressure and 20 degrees Celsius temperature is given, flows with a velocity of 8 meter per second over a flat plate. Flat plate's dimensions are given and the temperature is also given. So determine the rate of heat transfer for the plate when the air flows parallel to the 1.5 meter side. Yesterday, like the previous day, rather, we have done for part A where air flowed parallel to the 6 meter side, right? And now we will solve it for 1.5 meter side. Have any one of you done that?
Yes, ma'am.
What was the answer?
And it came out to be 4202.03 watts.
4.2. Okay.
Yes, ma'am.
It should come Around 8670. What did you get for the heat transfer coefficient?
Ma'am,
Heat transfer coefficient.
ma'am, it came out to 3.891.
Okay. There must be some mistake. Can you understand like where the mistake is? It's half.
Same.
Like what is the actual answer? It came to be half of that. Okay, tell me what is the Reynolds number for this when
Ma'am,
it is parallel to 1.5.
4.71 into 10 to the power 5.
Correct. So what we will apply? We'll apply laminar flow over here.
Yes,
And
ma'am.
for laminar flow, I have already shown you what the equation will be. That is 0.664. It will be, acha, have you applied 0.332?
Yes, ma'am.
That's what the problem is. Because this is it will be, Nusselt's number will be overall Nusselt's number. I have shown you
Okay.
yesterday, no? Yesterday also
Yes,
we have
ma'am.
solved that kind of problem. So it will be twice of the local Nusselt's number or the local heat transfer
Yes, ma'am.
coefficient. So just it will be 0.664, twice of 0.332. For laminar it will be twice, and for turbulent it will be 5 by 4.
Okay, ma'am.
Yeah,
Yes,
like
ma'am.
let me show you. We have seen na here the
Yes, ma'am.
overall see this is keen friction. For same will be happening for Reynolds number or sorry Nusselt's number, and even for heat transfer coefficient it will be same. That is for laminar it will be twice of the local, and for turbulent it will be 5 by 4 of the local. So here you have, that's
Okay,
why
ma'am.
you have got half the result of what the actual value is. So you have just to make it twice. That is
Yes,
Nusselt's
ma'am.
number will be 0.664, Reynolds number zero point 0.5, Prandtl number to the power 1 by 3. Okay.
Okay, ma'am.
Okay, then solve it. I'll solve it for you once. So first, I think the writing pad is visible. So first what we'll do, we'll calculate the Reynolds number. That will be velocity into the length of the plate, cause that will be the trailing edge, and this is the kinematic viscosity. So this will be 8 meter per second into 1.5 meter, 2.548 into 10 to the power minus 5 meter square per second. So this is 4.71 as you have already said, 10 to the power 5. This is correct. So this is 5 into 10 to the power 5, this is less than that. So what we will do, we will take laminar flow. So just 1 second. So laminar flow and length, for our length it is 1.5 meter. Okay. So cause it is parallel to 1.5 meter, the flow is parallel to 1.5 meters, that will be our leading edge. Now the flow is laminar and Nusselt's number is HL by K. But this is, remember, this is overall Nusselt's number. So this will be twice of local Nusselt's number, right? So this will be twice of 0.332, Reynolds number 0.5, Prandtl number 1 by 3. So this will come out to be 408. Now heat transfer coefficient, these
From
also overall.
doubt me where to use the overall Nusselt number and the
Yes, this
local
here,
Nusselt.
okay. Here overall length we have taken, right? So we have to
Yes,
take
ma'am.
overall Nusselt's number. If it was said that see this is the flow and there some at some place at some local place you have to find out the Nusselt's number, then we will take local Nusselt's number. But here it is said
Okay, ma'am.
that the to calculate the Nusselt's number for the overall range, that is for the overall length. So at that time you will take overall value, not the local one.
Okay.
Correct. So this is
Yes,
K
ma'am.
by L Nusselt's number. This will come out 0.02953 watt per meter degree Celsius. This is K upon L is 1.5 meter into 408 is the Nusselt's number. This is 8.03 watt per meter square degree Celsius. Okay. Now heat transfer rate is H AS Ts minus T infinity. So this is 8.03, 9, this is 9 cos this is 1.5 into 6, and this is 1, this is 140 minus 20. This will come out to be 8670 watt. Okay. Next is question number 14 for the previous day. Have anyone done this question?
I'm actually the new and the k is not given, so how to take those values?
Okay, is not given. Okay,
No,
no
ma'am.
problem. You do it now. K will be 0.0281. 0.0281 watt per meter degree Celsius.
Yes, ma'am.
Okay.
Yes, ma'am. And the new,
Nu will be 1.797 into 10 to the power minus 5. Okay, anything else?
no, ma'am.
Okay, solve it. Then we'll get back to it. So what it is said, let us get to the question once. Air at 15 degrees Celsius flows at 1.8 meter per second. So velocity is given, and over a heat, and so length is also given for the heating panel. And the temperature, that is the bulk temperature, is also given for the air. The panel is intended to supply 420 watt per meter square to the air. That is the heat flux is given. Okay, but the surface can sustain only 110 degrees Celsius without being damaged. So it is maximum temperature is given. So what is the maximum and average temperatures of the plate? That is the device, the panel that is supplying heat can sustain a maximum temperature of 110. So what will be the surface maximum plate temperature that it can be achieved? Are you solving? The
Yes,
equation,
ma'am.
temperature difference equation is also given, and the Nusselt number equation that we will be using for uniform wall heat flux is also given. Because here the panel is supplying heat to the air, right? And there will be constant heat flux that will be maintained here. So for the constant heat flux or uniform heat flux, we have already learned that concept in the class. I have already taught you. One concept is uniform wall heat flux, and another is uniform surface temperature. So this is the concept
Yes,
of
ma'am.
uniform wall heat flux. So the equation for that will be used is also given here. First, you can start with calculating what will be the heat flux. Like here, heat flux, we already know 420. That is the maximum heat flux that can be supplied by the panel. Right. So that can be corresponded to the delta T. So that will be the maximum temperature difference that can be maintained. And it is said that the surface can sustain about 110. So you have to see like how much close it is to 110. And from that delta T max, you can then get the wall temperature. And also here TW minus T infinite. So that equation is given temperature difference equation. So if we will put the value of TW over there, from that you can easily get the delta T, right? And you can easily relate it to delta T max, maximum temperature. From that you can easily calculate the back calculate the TW, that is the wall temperature. Are you solving it?
Yes, ma'am.
Okay.
Ma'am, is the maximum temperature 104.82 degrees Celsius?
Hmm?
And the maximum temperature
How much?
104.82.
Mm, no. The temperature that you need to calculate, right?
Yes, ma'am.
No.
Ma'am,
How you have
first,
calculated it?
ma'am, first,
Have you equated with like you will get the heat transfer rate, right? You have to equate that with delta T. And maximum heat transfer, you know, like how it should be, like what is the heat flux? 420. So if
yes,
you
ma'am.
will equate that with delta T, you will get the maximum temperature difference.
Yes, ma'am. Then it came out to. Then first I calculated the Reynolds number. Then I calculated the Nusselt number, and
Hmm.
then from that Nusselt number I calculated the heat transfer coefficient,
Hmm.
and then I put that heat transfer coefficient in that delta heat flux equation, and the temperature difference came out to be 89.82 degrees Celsius.
Ah, it is correct. Then,
And then the T infinite is 15 degrees Celsius. So from that I calculated the TW, which came out to be 104.82 degrees Celsius.
hmm, correct, correct, correct. Then, what we'll do? How to calculate the wall temperature?
And then that ma'am, in that equation,
Yeah, it's
the
already
average.
given. The equation is already given.
Yes, ma'am.
So, so you just put the value of QW in
Okay,
terms
ma'am.
of maximum temperature.
Yes, ma'am. And then we will find out the wall flux, wall
Yeah,
heat flux.
yeah. So that will be TW minus T infinite. T infinite you already know as 50.
Yes, ma'am.
So delta T also you will be able to get from this equation. So delta t, from delta t, delta t is tw minus t infinite. So from that tw you can get. Calculate that.
Yes. Yes, ma'am.
Yeah.
From
Yeah.
the heat flux, it came out to be 629.97 watt per meter square.
Heat flux. It's not
Yes,
required.
ma'am.
Heat flux you don't need to calculate, right?
No, no, the one.
You can directly put the Nusselt's number from there. Can you? See, let me show you. Let me show you. See, Nusselt's number is equal to QL by delta T max into K, right?
Yes, ma'am.
Hmm? We know
Yes,
this
ma'am.
already.
Yes, ma'am.
So if we will consider this heat flux to be maximum, that is already indicated in the question, then this will be delta T max. Okay. So from here we can write QL by K as Nusselt's number into delta T max, right? And
Yes, ma'am.
this is already present in the equation. If this is QW, this is already present in the equation, so we can directly replace this. And delta T max we know, and Nusselt's number we can replace from the that is already given, that is 0.4587, Reynolds number 0.5, Prandtl number to the power 1 by 3. Just replace this. So you can easily like cancel off the top and the bottom one. Understood?
Yes, ma'am.
Don't go for the lengthy process. It will make things simpler.
Okay.
Hmm. Okay, have you solved it?
And delta T max came out to be 89.82.
Delta T max max.
Yes,
Yeah,
ma'am.
that was correct. Your what your value of you have told me na 89
Yes,
point
ma'am.
something. It will be 89 point something. So it is correct.
Mm,
So it will, you will just put directly that value. And at the top it will be 0.4587 upon 0.688. Everything will cancel out now. From that you will get delta T, right? And T infinity you
That
already know.
is
From that you can get TW.
still confusing.
Ah, okay. Just wait. This part I'll show you. Other things are clear, right? So this
Yes, ma'am.
part only I'll write off because we have to proceed to today's questions. Just wait. Okay. See, delta T bar, what is given in the question? Just see whatever information you can gather from the question. So it's given delta T, that means TW minus T infinite, right? So that is QW L upon K, 0.688, Reynolds number half, Prandtl number 1 by 2, 1 by 3. Hmm. Now, this, as I've already said, you can replace this by this.
By yes, ma'am. The NUX.
Ha ha ha. This Nusselt's number form. So, this NU basically it is Hx upon K, right? And H you can write as Q is equal to H delta T, right? So, you can write Q upon delta T. Hmm? So, if you will write, like let me show you clearly. Nusselt's number is equal to Hx upon K. Hmm. So, now H we need to replace, H we don't need. So, we need what? We need heat flux. So, we will just replace this with heat flux. Now, heat flux is equal to H delta T. That is delta T means TW minus T infinity, right?
Yes, ma'am.
Now, NUX, listen, this is maximum, okay? This is the maximum heat flux. Because this we are taking as maximum. That is maximum panel, how much maximum heat flux it can like pass on. So this is
Supply.
Qmax, yeah. So Nusselt's number, if we will replace this is Q by Qx upon T W minus T infinity into K. Is it correct?
Yes, ma'am. Yes, ma'am.
Yeah. So this is nothing but delta T max if we will consider this as Q maximum, right?
Yes, ma'am.
Yeah. So now you have calculated the previous part. Now what you will do in this equation, we know it is QL upon K, right? So just you will do what here? If this is overall, if you will replace this as a overall, this will be overall Nusselt's number, right? So
Yes.
QL upon K you will just replace as, because here now we are not taking maximum, we are if this is maximum, then this is Nusselt's number into delta T max. This is QL upon K, because here we have taken overall heat transfer coefficient, heat flux, right?
Yes,
So
ma'am.
now we can replace this with this value, right? So what we will do, let me write it here, don't get confused, write this here. This will be delta T bar is equal to Nusselt's number overall. Remember this is overall because we have taken this as L, right?
Yes.
Whenever we'll take this L for the whole plate, that will be overall. So this is overall Nusselt's number into delta T maximum, the maximum temperature difference. So whether like if it may be local Nusselt's number or it may be overall Nusselt's number, the temperature difference will be same, right? So this will remain same. Now it will be, it is already given in the equation 0.688, Reynolds number 0.5, Prandtl number to the power 1 by 3, right? Now
Yes.
this we have already given in the question. Already it's given in the question as 0.4587. So this will be 0.4587. Reynolds number 1 by 2. Prandtl number 1 by 3. So 0.688 Reynolds number 1 by 2. Prandtl number 1 by 3. So this will be cancelling out.
Yes, ma'am.
And delta T max is there. Sorry, I missed that. Delta T max. Huh? So this will be simply 0.4587, 0.688 delta T max. This is delta T bar. So this is nothing but TW minus T infinity. Right, this is already given. And this value you will write here, and this delta T max. Delta T max we already have seen, it is 89 point. I got 6, but you got something 89, right? So
Yes,
this
ma'am.
will be here. So this value you can get easily. Now we need TW. TW will be 15 plus this whole value. Understood? Any doubt?
Yes, ma'am. No, ma'am.
Yeah, because if we will, you can obviously calculate the heat, like heat transfer rate and everything, but and also heat transfer coefficient. But what it will do, it will just complicate the things, right?
Yes,
And in that long process of calculation, information will be lost. So whatever will be asked, try to keep every of your like whole formula. You try to take in that values. Like here what we did, we don't need heat transfer coefficient, right? Let me use some other color. Yeah, here we don't need heat transfer coefficient, right? Because heat transfer coefficient is not asked. So what we have done, we have just replaced heat transfer coefficient with the heat transfer rate, heat flux rate rather. So heat flux rate is given in the question, so we have used it here. Now in the next question, we need what we need, what value we have, we have delta T max value, right? So delta T max value we have simply used here. Even Q, this value also you can use, it's your wish. But rather I have just, for the simplicity, cause Nusselt's number equation we can directly get from the question, right? It's already given and we can cancel out. So that's why I've just replaced it with uh, Nusselt's number and the maximum temperature, right?
yes, ma'am.
So try to shorten the answers. So like in gate kind of exams, right? You have like only 1 minute to solve this question, only 1 minute. So you have to shorten it up, because you don't have time to calculate all those lengthy questions like H and then Q. You don't have that much time, so try to shorten things up.
Yes, ma'am.
Okay, have you understood this?
Yes, ma'am.
Okay, then let's proceed to the today's questions. Okay, so for the first question of today's class, as a means of preventing ice formation on the wings of small private craft, like when the outside temperature is minus 23 degrees Celsius. So there is as the flight is moving in such a high like velocity, so obviously there will be chance of uh, uh, like condensation of the water vapors that is available on the atmosphere, and there will be like chance of formation of ice at such a low temperature. So what some company have done, they have proposed the electrical resistance heating elements to be installed on the wings. To determine the representative power requirements, consider nominal flight conditions to which the plane moves at 100 meter per second in here. That is at a temperature of minus 23 degrees Celsius. As I've already said, the ambient temperature is minus 23 degrees Celsius. If the characteristic length of airfoil is 2 meter, so just consider this as a plate. You can consider that. And its length is given as 2 meter. And wind tunnel measurement indicate an average friction coefficient. Friction coefficient is also given for nominal condition. Choose the closest value of average heat flux needed to maintain a surface temperature of 5 degrees Celsius. What will the average heat flux? This is very easy, right? You have the like You don't need to consider even the plate. Here, friction, average friction coefficient is given. So from that, you can back calculate the other values, right? Hello?
Yes, ma'am.
Yeah, you can back calculate that. You can use here Reynolds analogy like this one. Let me show you. This analogy you can use.
Yes, ma'am.
This is basically what is the Chiltern Colburn? This is Stanton number into Prandtl number to the power 2 by 3, right? And Stanton number means Nusselt number upon Reynolds number into Prandtl number. So you can just simply use this. So what this will give? This will give a correlationship between skin friction and the Nusselt number, right?
Yes, ma'am.
So just one second. Let me note down the Reynolds one second. You solved this question.
Ma'am, no question.
Yeah. Oh, just one second. Hmm. Okay, so what I was saying that if you calculate the Reynolds number, the values are already given here. If Reynolds number you calculated, then you skin friction you know. So from the analogy, you can directly calculate the Nusselt number, right? And if you know the Nusselt number, then you can calculate the heat transfer coefficient, and from there you can easily get the heat flux.
Yes.
Correct? Yeah, do that. I'll just come in 1 minute to solve this.
Ma'am, that new must be given.
No, is not given. Just one second. I'll write it down. Equation number one. See, these two values were missing. I've given this. Okay. Now you can do it, right? Just use the skin friction coefficient is given. From that, you can directly correlate the Nusselt number. And from the Nusselt number, obviously, you can, if you know the like Reynolds number, you can directly calculate from every value. And then you can calculate the from Nusselt number, you can get the heat transfer coefficient, and from the heat transfer coefficient, you can get the heat flux. That is already like this is only asked in the question. Okay, let me do one thing. Let me draw the diagram for you for your uh, understanding the problem. Let's suppose this is the fin. Okay, here the electric heater is there, and this is the airfoil. Surface temperature is 5 degrees Celsius, and skin friction is given as 0.0025. And the whole length is given as 2 meter. So along this length, the airflow will be taking place, right? And this is air. This will flow in this direction. The ambient temperature is minus 23 degrees Celsius. How's this direction? This direction. So this is velocity is 100 meter per second given. Okay. Now you can solve it, right? I'll come in 1 minute. You solve this. Anyone solved?
Solving.
Okay, okay, okay. I'm here only. If you'll solve, then ping me up.
And to calculate the heat transfer coefficient, we need the K value.
K value. Just one second. Mhm. K value will be 0.022 watt per meter Kelvin. 0.022.
Ma'am, I think the answer is option B.
Yeah, yeah, correct. Okay. I'll just give a bit details. I won't be going to the in detail solving because this will just take more time. Okay. So first, as I've already said, we will use Chilton-Colburn equation analogy, right? So this is Stanton number, Prandtl number to the power 2 by 3. This is Nusselt's number, Reynolds number, Prandtl number to the power 2 by 3. So this becomes Nusselt's number, Reynolds number, Prandtl number to the power 1 by 3. Reynolds number, when you will find it, you will get 1.23 into 10 to the power 7. Hmm? Now, Nusselt's number is equal to CF upon 2, CF bar upon 2. What is this? This is Reynolds number, Prandtl number to the power 1 by 3. Okay. So, this is how much? This is 0.0025. Reynolds number is this one and Prandtl number is 0.72. So, this comes out to be 13780. Now, heat transfer coefficient is K upon L Nusselt's number, right? Because Nusselt's number is equal to HL by K. So, H is equal to KL into Nusselt's number. This is 0.022 upon 2 into 13780. So, this comes out to be 152 watt per meter square Kelvin. Always remember to give the unit, okay? So, heat flux is heat transfer coefficient into Ts minus T infinity, right? So 152, 5 minus 23. So this is 4260 watt per meter square. This is option B. Okay, right? Let us proceed to question number 2. The dimensionless temperature profiles and heat flows in unsteady state heat conduction may be expressed in terms of following two dimensionless number. This is the third class, like third or fourth. In fourth class we have undergone these problems, right? Just tell me which of the option is correct. In dimensionless temperature profiles, like where unsteady state heat flows have been, there is lump parameter model. Which of the two dimensionless number we have found out? In
Ma'am, option A.
option A, yeah, correct. So this is option A. Now let us proceed to question number 3. Hmm. So hot liquid is flowing at a velocity of 2 meter per second through a metallic pipe having an inner diameter of 3.5 centimeter and length of 20 meter. The temperature at the inlet of the pipe is 90 degrees Celsius and data are already given here. Find the heat transfer coefficient for inside flow inside the tube. And the correlation for Nusselt's number is given as 1.86, Reynolds number for laminar flow, Reynolds number Prandtl number d by L whole to the power 1 by 3, and for turbulent flow it is 0.023, Reynolds number 0.8, Prandtl number to the power 0.33. The options are given. So what will be the correct option, correct value for the heat transfer coefficient? You will just use the flow through a pipe, like sir have already taught you, na? So you will first calculate the Reynolds number, you check which of the equation is applicable, use that equation and then find out the corresponding heat transfer coefficient for Nusselt's number. Any doubt? Solve this. If you are having any doubt, then do ping me. I'm here only. Unmute yourself and ask me the question.
Ma'am, is the Prandtl number given in the question?
Prandtl number, it's indicated, no? is very unlikely. Just 1 second. Oh, Prandtl number you can calculate. CP is given, right?
Yes, ma'am.
Prandtl number you can calculate.
Okay.
Yeah, tell me.
I'm calculating.
Okay.
And my answer is not coming.
Hmm. Why? Tell me where you are facing the problem.
First, I calculated the kinematic viscosity, that is mu by rho.
No, kinematic viscosity is not required to calculate, right?
But Reynolds number we have
Ah,
to
you
find.
you just directly write mu and rho.
And then Reynolds number is calculated V into L by mu.
Huh?
And
Yeah,
then
continue.
it came out to be turbulent.
Ah, correct.
And then
What is the value of Reynolds number?
from 1492.53 into 10 to the power 5. Yes,
You
in
tell
that
me
way.
what the D is. Reynolds number is what? Reynolds number is rho b d upon nu, right? What is this d? What is the value of that?
3.5 into 10 to the power minus 2.
Correct. 0.035. And then what is this velocity?
2 meter per second.
Density?
950 kg per meter cube.
Kg per meter cube. Then
Yes.
mu?
U is 2.55 into 10 to the power minus 4.
So if we will calculate this, it will come out to be 260,784.3. You just recheck it once, huh? So this is turbulent, right? Greater than 2300.
Yes, ma'am.
So then Prandtl number you have to calculate. Prandtl number what you have done?
Ma'am, CP mu by K.
So mu Cp by K, mu is given as 2.55 into 10 to the power minus 4. Cp is 4.23 into 10 to the power 3, right? Is
Yes,
kilojoule, huh?
yes, ma'am.
Then K is 0.685. So this comes out to be 1.57. What you got?
Yes, ma'am. Yes, ma'am.
It is right. So then Nusselt's number, what you will take? You will take the second one, right? That is 0.023. This is the Hitler's Bolt temperature. So this
Yes,
is
ma'am.
Reynolds number to the power zero point 0.8, Prandtl number to the power 0.33. Correct?
Yes,
So
ma'am.
this Reynolds number you already know from here, Prandtl number you know, so you can calculate this. What value did you got from it?
574.65.
Just one second. Yeah, correct. So this will be 574.65. Now this is what hd by k. So from here you will get h. H will come out to be 11.246 kilowatt per meter square. So this is which one? This is option number D. Correct?
Yes,
Where
ma'am.
did you face the problem?
And that Reynolds number.
Uh,
And actually, I did not use this formula. I used separate one. So,
huh?
and I used a separate formula. It is V into L by mu. So, from that it came out to be different.
V into L by mu. Acha, length you have used, but here the heat transfer will be from the diameter, no?
Yes,
Heat
that's right.
transfer will through the diameter, like in the diameter direction, because it will be from hot liquid to the outer side.
Yes, ma'am.
So the D will be used here rather than L.
Yes,
Length
ma'am.
won't be used here. Yeah. Okay. Now next question. So this note down these formulas. So we'll be using it later on. So for fully developed flow, as I've already said, you have already learned in the class the constant wall heat flux terminology and what happens there. Like if let's suppose a pipe is there and water is flowing inside, like little bit any liquids may be flowing inside, right? So and we have maintained, we have looped around like heater through the whole pipe. So what will happen? We can maintain constant heat flux there because the heat flux on every direction will be same. So it will be constant. So this is the constant wall heat flux phenomenon. And constant surface temperature means the whole surface temperature. Like let's suppose there is a coolant that is running through the outer side of the pipe. So if a coolant is running and the heat hot liquid is flowing inside. So what will happen, there will be condensation on the wall. So if there, we know that when phase change will take place, so the temperature will remain constant, correct? So this will give a phenomena of constant surface temperature. So for constant surface temperature, for fully developed flow, if we maintain the constant heat flux, we can use this formula, and for constant surface temperature, we can use this formula. You may or may not use this later, but this will be very applicable for you in the further, like if you want to solve gate problems and everything. So these two formulas are very essential. And another Dittus-Welter equation, this is like obviously very hugely used. So for fully developed turbulent flow, we will be using Dittus-Welter equation, that is Nusselt number is equal to 0.023, Reynolds number to the power zero point 0.8, Prandtl number to the power 0.33. Have you noted it down?
Noted.
Do tell me after you complete so that I can shift to the next question.
Done. Done.
Done. Okay. So next question is, for a turbulent flow in a pipe, the heat transfer coefficient is obtained from Dittus-Welter equation. If the tube diameter is half and the flow rate is double, what is happening? Tube diameter is half, that is D is half, and the flow rate is double for the new flow. The heat transfer coefficient will change by what factor? We will be using Dittus-Welter equation. Just break down every, like Reynolds number and Nusselt's number, you break it down. So you will get like where D is there and where flow rate is there. Because velocity you can directly correlate to flow rate, right? So from there you can see like what is the ratio of Q2 upon Q1 or D2 upon D1. From that you can see the heat change of heat transfer coefficient on the second case, that is H2 as compared to H1, by a factor like H2 upon H1 is asked here, right? Have you understood the question?
Yes, ma'am.
Okay, okay, solve it then.
Ma'am, I'm taking a small break.
Okay, okay, sure, sure.
Is the answer option C?
Option which one?
Third option.
Yeah, correct. Okay, so let us get a brief of this. So this is question 4, right? So first Q2 is equal to 2Q1, it's already given. D2 is equal to 0.5 D1. Reynolds number is equal to dV rho by nu, and V is Q upon A, and A is pi D square, right? So dd cancels. So this is Q upon D. This is proportional to Q upon D. Okay, that RE2 upon RE1 is equal to Q2 upon D2 upon Q1 upon D1 is equal to 2 upon zero point 0.5. This is 4. Now, heat transfer coefficient is proportional to Reynolds number to the power zero point 0.8 upon D. So, this is H2 upon H1 is equal to RE2 upon RE1 to the power zero point 0.8 upon D1 upon D2. So, sorry, this is multiplied by D1 upon D2. Just one second. Because this is upon D, right? So, this is 4 to the power zero point 0.8 into 1 upon zero point 0.5. So, this gives 6.1. This is option C. Now, let us proceed to question number 5. The layer above laminar sublayer which experiences the effect of both viscous and turbulence is called which of the following?
Option C.
Yeah, above first one. So, next question. The boundary layer is an interesting concept wherein the effect of viscosity could be realized in experience. On such an aspect of boundary layer is that even when an incoming flow of flat nature, flat impinging velocity profile, the velocity and temperature distribution within the boundary layer are two-dimensional. True or false? Basically, it simply denotes that flow in the boundary layer is one-dimensional or two-dimensional or three-dimensional. Here, Z has been considered as infinitely long. So it will be, flow will be in which directions? Hello?
Ma'am, it only flows in one direction.
No, no, it will be in two direction, right? In y direction, like not flow, like the temperature distributions in will be in two direction, no? Velocity and temperature distribution.
Yes, ma'am.
It will be x and y both directions.
Yes, ma'am. Yes, ma'am.
So there will be momentum diffusion and thermal diffusion in both directions. So it will be
Wait.
which of the following? It will be A. True. Okay.
Yes, ma'am.
The product of Grashof number and Prandtl number is which of the following? Grashof number, natural convection, sir, I have not taught in the class.
No, ma'am.
Okay, okay. Then it will be Rayleigh number. Okay.
Ma'am, option A. Yes, ma'am.
Yeah, it will be Rayleigh number. Sir will teach you later on. So in natural convection, we'll get the term Rayleigh number. That is where we get Nusselt's number. No, there we will get Rayleigh number.
Okay, ma'am.
Okay. Then we come to next problem. That is for a particular engine, the underside of crankcase can be idealized as a plate measuring 80 centimeter by 20 centimeter. The engine runs at 80 kilometer per hour and crankcase is cooled by the air flowing past it at the same speed. Due to the road-induced vibrations, the boundary layer becomes turbulent from the leading edge itself. The temperature at the crank surface is 75 and the ambient is 25, and the properties are given. So these are the information that has been provided for question number 8 and 9. So here the dimensions of the plate, simply leave everything else. The plate, one plate is given, and this is the flow over a plate, and the dimensions of the plate are given, and the velocity at which the fluid flows is 80 kilometer per hour. That cause it is said that air is flowing at the same speed. Now, the temperature of the surface is given as 75, and for the ambient is given as 25, and all the other things are also given here. Now, what is said? It is said that we have to first find the value of the Nusselt's number, and it is closest to which of the following. Have you understood? Can you calculate it?
Yes, ma'am.
Yeah, yeah. And Nusselt's number formula is also given, that will be used here. Okay,
Okay.
calculate this. Problem is similar only what you have already done.
And can you show the options? Ma'am, I guess it's option B.
Hmm. Okay, correct. Next question, can you solve it? It's related, right? The heat loss by the crankcase will be closest to which of the following? Nusselt's number you have got, then you can easily calculate the heat lost.
Yes, ma'am. Ma'am, the question. And the main question, can you show that? Ma'am, the options. Ma'am, is it option C?
Yeah, option C. Okay, then let us get on with the solution. You have already solved it, so I'll just give a briefing of that. First, we will calculate the Reynolds number. So Reynolds number will come out to be 990306. That is greater than 5 into 10 power 5. So because it is flow over a flat plate, right? So now for turbulent flow, Nusselt's number is equal to 0.036, Reynolds number zero point 0.8, Prandtl number 0.33. So this comes out to be 2002. That is option B. Now, for the question number 9, Nusselt's number is equal to HL by K. So H is equal to Nusselt's number K by L. So 2002 into 2.824 into 10 to the power minus 2 upon zero point 0.8. So this is 70.6. Now Q is equal to HA delta T. This is 70.6 into zero point 0.8 into zero point 0.2 into 75 minus 25. This comes out to be 564.8 watt. This is option C. Now we'll go for question number 10. Okay. The Cedar-Tate equation is valid only for the case of constant surface temperature. Is it true or false? Have you learned about Cedar-Tate equation? It's used in turbulent flow, right?
Yes, ma'am.
So it is used for constant surface temperature or not? Is it valid only for that only? Remember, Cedar-Tate equation 0.023, Reynolds number zero point 0.8, Prandtl number 0.33, mu upon mu w to the power 0.14. Now tell me whether it is used only for constant surface temperature, or it can be used for any case. Tell me.
I'm confused.
Okay, it can be used for any case. Basically, what happens here, we take into consideration the dynamic viscosity difference between wall and fluid. What happens? Dittus-Boelter equation, we do not consider mu upon mu w into consideration, right? Why? Because we take the temperature difference between the wall and the fluid to be very small. So that's why there won't be much variation in the dynamic viscosity. But in case of Cedar-Tate, when the temperature difference is very large in between the fluid and the wall, we take the equation of Cedar-Tate. And it is valid under any circumstances for the turbulent flow, right? It is not for constant surface temperature. It is valid for any circumstances. Okay, then question number 11. We have three more problems, not simple question, these are problems. Okay, so question number 11. In a wind tunnel experiment, air at 20 degrees Celsius is moving at 15 meter per second, is warmed by an isothermal steam heated plate at 110 degrees Celsius, half meter in length and half meter in width. So the plate dimensions are given as half and half, that is 0.5 meter, 0.5 meter. And so it is a square plate and it is at 110 degrees Celsius. Isothermal steam heated. So it is at constant 110 with it. So this is a condition of constant heat surface temperature, constant surface temperature condition, right? Because it is isothermal steam heated plates. As it is steam heated, the temperature will remain constant. So, and the bulk air temperature is given at 20 degrees Celsius and velocity is also given. Find the average heat transfer coefficient and the total heat transfer. And what are H, delta T and delta at the trailing edge. So what are these? Consider that. So this is flow over a flat plate. Mind that. Okay. So first what we need to do, we obviously in this all of these type of questions, and consider see, it is already given, you find the Reynolds number, but it's already given the wind tunnel as low turbulence. So the flow ought to be laminar up to trailing edge. So it is already said that flow will be laminar, whether the Reynolds number is greater than 2300, or sorry, 5 in 10 to the power 5 also, it will be like it is laminar. So it should be, Reynolds number should be less than that, 5 in 10 to the power 5. Hello? You understood,
Yes, ma'am.
right?
Yes, ma'am.
Reynolds number will come less than that.
Okay, ma'am.
So first find the Reynolds number, and again the same way we will for if it is laminar or it is turbulent, it is already said laminar during the question. So what we will use, we'll use twice of Nusselt's local Nusselt's number. So that average Nusselt's number we can get. From average Nusselt's number we can get the heat transfer coefficient, and from that we can get the heat flux. And also delta for laminar flow, delta also we know, delta T also we can get, right? Everything you can get, cause delta upon delta T, again we know that Prandtl number to the power 1 by 3. So use these analogies to get the things that are being asked in the question. Sorry. If you face any doubt, do tell me. Uh, I'll just come back in 1 second. Okay, you solve it. Like in 1 minute, I'll be back. Have you solved it? Hello?
Yes, ma'am. The
What was the
the
score?
ma'am age came out to be 21.394.
20, how much?
21.394.
No, no, no. It will be, see, 21.4 is overall, but you have to find the local one also, na? At the trailing edge. So it is the local.
Yes, ma'am.
Understood. So local one will be half of that because overall we can find out, right? From the all the values that are given. So that will give us overall heat transfer coefficient, and also the local heat transfer coefficient also we have to find out, right?
Yes, ma'am.
And at the trailing edge, yeah, at the trailing edge means at x is equal to L. Yeah, it is overall only. Overall we find out, and also a local one we find out. And what you got for the delta, the film thickness?
Ma'am, that I did not calculate. I'm calculating.
Yeah, yeah. It will take you 1 minute. For laminar flow, I've already given you formula previous week, na?
Yes, ma'am.
Just put on that formula. Have you calculated? Hello?
I'm doing
Okay. Let me solve the initial part. So Reynolds number will come out to be 384. That is, it is u infinity L upon nu. Right. So it comes out. It will come out to be 384,600. Then we'll calculate the Nusselt's number, that is twice of local Nusselt's number. This is overall Nusselt's number. This is twice of 0.332. Reynolds number 0.5, Prandtl number to the power 1 by 3, because it is laminar flow, right? It is less than 5 into 10 to the power 5. So this will overall Nusselt's number will come out to be 366.2. And then heat transfer coefficient, overall heat transfer coefficient will be Nusselt's number into K by L, right? So it will come out to be 21.4 watt per meter square Kelvin. Uh, you have got these values only, right?
Yes, ma'am.
Okay. Then heat transfer rate, it is overall heat transfer coefficient into area into delta T. That is 21.4 into zero point 0.5 square. Area is zero point 0.5 square because it is a square, right?
Yes, ma'am.
The plate is a square and its one side dimension is zero point 0.5 meter. And this is 110 minus 20. 20 is ambient temperature and this is the surface temperature. This came out to be
Yes, ma'am.
482 watt.
Yes, ma'am.
Next is
Ma'am, the
del.
ma'am, the delta came out to be 4.029, and
4.0, oh, similar, yeah. And
and
then
the
the,
delta T 4.534.
hmm, yeah. So then, as I said, local one also you'll calculate local heat transfer coefficient. That will be 10.7. That is half of this overall heat transfer coefficient. This one, right?
Yes, ma'am. Yes, ma'am.
And then delta at x is equal to L, that is at the trailing edge, will be 5 into L into root over REL. So this will come out to be 3.97 mm. And delta T is, we know that delta upon delta T is equal to Prandtl number to the power 1 by 3.
Yes, ma'am.
Okay, so this will be delta upon delta T is equal to Prandtl number to the power 1 by 3. Okay, so Prandtl number, so that is delta T is equal to delta upon root over Prandtl number, cube root of Prandtl number,
Yes,
right?
ma'am.
So this is 3.97 upon cube root of Prandtl number is 0.703. This will come out to be 4.46 mF. Yeah, so we got all the values. Now let us proceed to the next question. We have 10 minutes left and we have two more questions. Let's see how much we can do. Okay. So this is a wind tunnel, and here we will get the combination of all the layers, that is turbulent, laminar and transition. And the equations that we'll be using also given here. In a wind tunnel experiment, an aluminium wind tunnel, okay. So this is not water, only water. So we have to consider all the laminar flow also, turbulent flow also, and transition flow also. So here it is said that an aluminum plate of 2 meter in length and 1 meter width is held at a temperature of 310 Kelvin and is cooled on the surface by airflow at 10 meter per second. The air in the wind tunnel has a temperature of 290 Kelvin and is at 1 atmosphere pressure. Okay. So the air temperature is given and the surface temperature of the plate is given. So this is a flow over a flat plate. The Reynolds number at the beginning and the end of the turbulent transition regime is observed to be 4 in 10 to the power 5 and 8.7 in 10 to the power 5. That is here all the there will be all the flows, that is here laminar, then turbulent, and sorry, transition and then turbulent. So this is laminar, then transition, then turbulent, right? So it is said that this is the from laminar to transition it is 4 in 10 to the power 5, and from transition to turbulent it is 8.7 in 10 to the power 5. Hmm. Uh, okay. What is the what is the heat loss from the plate? So we have to find out Q. The other values are given. Even the Nusselt's number is also given. The whole equation is given for gases. Here for gases only we are finding out, and see also how to calculate. You it is you can find out. REL is the Reynolds number for the laminar region. Okay. RE small l is for the laminar region, and the capital L and U. This is the lower and upper regime of the transition. That is, this L is the lower one. This is REL and this is RE. Okay. Any doubt? This simple equation is also given. Everything is given the same way as you have done other question. You will just simply calculate it. Understood?
Yes, ma'am.
Okay. Calculate this. I'll be just back in 1 second. If you are having any doubt, unmute yourself and ask me the question.
And that RE small L we have to find out.
Which one?
And RE small L.
Aries small is the laminar regions and all somewhere. Na? You have to find out that. Velocity is given, so you can directly find out that.
Ma'am, but that RE is not coming to be laminate fraction.
What is this coming?
12.69 into 10 to the power 5.
Mm, now what you have taken? Oh,
Ma'am,
it is
RE
coming out to
cost.
be 10 to the power 6, right? You can use that only. You
Okay,
can use
ma'am.
that.
Okay, ma'am.
Just pin it in the formula that are given. Have you solved it or are you facing any doubt?
Ma'am, the calculation is a little long, so that's why.
Okay, fine. Go ahead.
Ma'am, is the answer 114.8 watts?
114. No, no, no. There'll be three parts. Have you done all the parts?
No, no, it's for cal.
Here, REL that we will calculate
Yes, ma'am.
will come out to be, like, this is 10 into 2 upon 1.575 into 10 to the power minus 4.
Yes, ma'am.
Correct? This will come out to be 1.27 in 10 to the power 6. REU, that is the upper limit, is 8740 zeros. And REL, that is the lower limit, will come out to be 4 into 10 to the power 5. Oh, just wait. 1 second, 1 second, 1 second. Why the calculation is stuck? Transition path. Sorry, sorry, one mistake. This will be my mistake. So this is L, right? Cause this is less than 5 in 20 power 5. So we'll use this for the laminar flow, huh?
Yes,
For the
ma'am.
laminar
Yes.
part. Yeah. And this what we have calculated, this is for the transition part. That is, we can consider this as REL, capital L, for the transition region and for the turbulent region as well. So for the turbulent region, we'll be using this as it is greater than 5 in 10 to the power 5. Yeah, for turbulent region, we'll be using this. So we will consider this as RE capital L. Hmm? And REU is already, this will remain the same. So this mu bar HL upon K, this is 0.037, Prandtl number zero point 0.6, and this is REL zero point 0.8 minus RD U zero point 0.8. This U is this one, that's at first part is for the turbulent flow, right? So for the
Yes, ma'am.
turbulent flow, as this is greater than 5 into 10 to the power 5, so this will be using for the turbulent flow. That is, we'll be using here in place of REL. And for RU, obviously it will be 8740, four zeros, right?
Yes, yes.
This is the upper limit of the transition flow. And for the rest of the thing, it is simple. For RE small l, this is the 4 into 10 to the power 5. This is the lower, this is the this is the start of the transition region. So this is the laminar part. This is the laminar part, and for the laminar part, this 0.664 for the laminar part, we'll be using this because this is less than 5 into 10 to the power 5.
Yes, ma'am.
So this will be using for the laminar part, and then for the last part, that is for the transition part. For the transition part, this is REU, that is in place of U will be using 8.7 in 10 to the power 5, And for REL will be RE small l will be using which one? That 4 into 10 to the power 5, right?
Yes, ma'am.
The same thing that we are using here. Now it is clear?
Yes, ma'am.
My mistake. So sorry for that.
And the
And
final
next,
answer will be what?
yeah, you calculate that. It will take 2 minutes to calculate this. Just put it on the calculator and tell me the final answer. First, what you will do, don't calculate it altogether. Calculate the turbulent part, calculate the
Yes,
laminar
ma'am.
part, and calculate the transition part. Then you will see that how much each layer like pays into the final contribution. Like how much each of the layer contributes to the final value.
Yes, ma'am.
Whether transition part plays more or the turbulent part plays more or laminar part plays more. Check that. And then when you will get the final Nusselt number, from there you can calculate the heat transfer coefficient, and from there you can easily calculate the heat transfer. Okay, do that. Have you done it?
No, ma'am. Calculating.
Okay. For clarity, let me write down the equation for you. C we will calculate as 0.9922 log 10 of the laminar Reynolds number, because it is said what C is Re small l. So small l is the lower value of the boundary layer. That is a turbulent transition regime. The lower value is 4 10 to the power 5. So this will be the lower value minus how much? 3.013. So C will come out to be 2.55. And RE capital L, that is the transition Reynolds number, that is this will be in the turbulent regime. So this is 10 to the power 2, 1.575 into 10 to the power minus 5. This is 1.27 into 10 to the power 6. Right? Now the Nusselt's number. Average Nusselt's number is given as 0.037, Prandtl number zero point 0.6, Reynolds number zero point 0.8 minus Reynolds number upper limit 0.8. So this will come out to be this value 1.27 in 10 to the power 6. This is for the turbulent zone, right? So for the turbulent zone, the lower value will be 1.27 10 to the power 6 and the upper value will be 8.7 in 10 to the power 5, right?
Yes,
Now,
ma'am.
yeah. So now then the laminar part comes in. So 0.664 into the laminar boundary layer, like laminar part Reynolds number. So this will be 4 into 10 to the power 5 half and 0.70 Prandtl number to the power point 1 by 3. Now C came out to be 2.55 and this is 0.0296. This is the upper Reynolds number. 8.7 into 10 to the power 5.8. Our Prandtl number is 0.708 to the power 0.6. Okay. Then minus 0.332, 4 into 10 to the power 5.5 and 0.708, 1 by 3. This is the this is also given the lower part, the laminar Reynolds number. So this is 4 into 10 to the power 5. Correct. So if we will solve everything like here, the first part will gather some value. There is the turbulent part. Then laminar part will gather some value. Then the transition, this whole transition part will gather some value. So tell me these values, then we can calculate the final value. What you have got?
And for the turbulent part, I got 598.49.
Hmm.
And then for the laminar part, 374.291.
Hmm. Then
Then for the transition part, I got 460.094.
hmm. 460.094. Right.
Yes, ma'am.
So yeah, so this will approximately come out to be 1433, and we
Yes,
can
ma'am.
also see all of them are almost similar. That means the contributions of the turbulent, laminar and transition are of similar size, right? All of them
Yes,
will
ma'am.
be equally contributing to this whole turbulent transition regime, right?
Yes, ma'am.
That we needed to, like, if some other question arises from this particular question, then we can answer that. So in this type of question, remember to separately calculate, and then you will just club it up. So
Okay, ma'am.
Nusselt's number into K upon L. So this is 1433 into 0.0264. K is 0.0264 upon L. L is how much? L
2 meters.
is 2, right? 2 meter in length. So this will come out to be 18.92 watt per meter square Kelvin.
Yes, ma'am.
Now the convective heat loss from the plate, this is the heat transfer rate, this is HA delta T. This is 18.92 into 2 into 1 into 310 minus 200. This is 756 watt.
Yes, ma'am.
You got this answer?
Yes,
What
ma'am.
answer did you got?
756.56
Ah,
watts.
okay then. Okay, so it's only 9:15. I think I should show you the last question and I'll give you this as homework. You try to solve it. This is relatively simpler question. You try to solve it. I'll show you this solution in the next one. Okay.
Okay, ma'am.
So for this, water is to be heated from 15 to 65 degrees Celsius. Water will be passing from inside the pipe. This the pipe is the internal diameter of the pipe is 3 centimeter. It is 5 meter long. The tube is equipped with an electric resistance heater that provides uniform heating through the surface. Right. So the constant heat flux is given, as we can see in the diagram also. The outer surface of the heater is well insulated so that the steady operation and heat generated in the heater is transferred to the water in the tube. If the system is to provide hot water at a rate of 10 liter per minute, determine the power rating of the resistance heater. You understood what we need to do, right? Also estimate the inner surface temperature of the pipe at the exit.
Ma'am, can you simplify a bit?
Okay, so here we have, like, we all already know, like, we already studied about the constant heat flux. So here constant heat flux phenomenon will be applied. So now surface area we can calculate through which the heat transfer take place, that is pi dl. So pi dl will give us the surface area. Now here we have the volumetric flow rate. So if you have the volumetric flow rate, see here Cp is given and volumetric flow rate is given, that is 10 liter per minute. So we can clearly calculate the mass flow rate, right? From volumetric flow
Yes,
rate, we
ma'am.
can calculate the mass flow rate. So from the, if we calculate the mass flow rate, because density is given. So mass flow rate, we, if you can calculate, so from mass flow rate, we can directly apply MCP delta T, because temperature difference is also given. And it's
Yes, ma'am.
already said na that uniform, like see, where it is said that heat yeah, yeah, yeah. It is already said that uniform heat flux is there. So if uniform heat flux is there, MCP delta T we can apply here. So
Yes,
MCP delta T, from MCP delta T we can clearly find out the heat transfer rate. That is
yes,
already
ma'am.
that gives the uh, first first question answer. Determine the power rating of the heat resistor. See how much
Yes,
heat
ma'am.
will be transferred into the water. That will be the heat that is being generated or being transferred by the resistance heater, because that is only transferring the heat, and there is
Yes,
no
ma'am.
like opposite direction. There is no transfer of heat, right? There is no transfer of heat from the heater to outside. There is only inside transfer. So
Yes, ma'am.
this heat transfer rate will give the power for the that will be equal to the power, the power rating of the resistance heater, correct?
Yes, ma'am.
Okay, this has gone with the first part. Now what is said, that also estimate the inner surface temperature of the pipe at the exit. Okay, just 1 second, I'll tell you about that. Okay, okay then. See, heat transfer rate we know, and from heat transfer rate, if we apply H delta T, we can apply that easily. And if we
Yes, ma'am.
apply H delta T, this Q we already know, that is if we do Q upon, that is, if heat transfer rate we have already found out, right? Heat
Yes, ma'am.
transfer rate upon the surface area through which heat transfer takes place is pi d L.
Yes, ma'am.
This pi dl will give us what? Heat flux. And
Yes,
heat
ma'am.
flux is equal to H delta T.
Yes, ma'am.
That is the surface temperature minus the mean temperature of the water. That is when it is like the heat, there are three parts, right? First from the heater to the surface to the mean water,
Yes,
right?
ma'am.
So first part is completed. From there we got the Q, and that Q will only be transferred to the water body, right? So if we will divide it with the surface area, then what we'll get? We'll get the heat flux, and
Yes,
that
ma'am.
will be equal to H into Ts, that is surface of the pipe, to the mean temperature, mean water temperature, Tm,
Yes, ma'am.
right? And what is said? Ts we need to calculate. So for that, what we need? We need Qs, that is the heat flux. Heat flux I already told you how to calculate. Now what we need to calculate? We need to calculate the mean temperature. So how we will calculate the mean temperature? For that, there are many steps. Let me give you in detail. Just 1 second. Okay. First, what we'll do? We'll calculate the Reynolds number. So we know the volumetric flow rate. From there, we can get the velocity, and from the corresponding velocity, we can get the Reynolds number. Okay. Based on
Yes,
that
ma'am.
Reynolds number, we can get the, this is the pipe, right? So we have to first understand in a pipe flow that whether it is developed flow or undeveloped, like non-developed flow. So if it is not developed, then there will be one equation of laminar turbulent flow, and if it is developed, then there will be one equation, right? So
Yes, ma'am.
for pipe flow, first we need to know the entry length. So if we will get the Reynolds number, from that, and we will get, from that we can calculate the Nusselt's number and all. But first we need to calculate the entry length, and for pipe we know that 10d is the entry length for turbulent flow or laminar flow in case.
Yes, ma'am.
So if it is laminar flow, then what we will be doing? It is I guess Reynolds number into D, right?
Yes,
Something
ma'am.
like that formula is there. So you just check it out. Sir have already taught that in the class. So
Okay, ma'am.
first we will find out the entry length, and we will see based on Reynolds number which formula we will apply for the entry length. That is whether for laminar flow we will apply and for turbulent flow we will apply. So once we
Okay.
will get the entry length, then we can easily understand the like whether it is developed flow, fully developed flow, or it is not fully developed. And if
Okay.
it is fully developed flow, as in this question, it will come as fully developed flow only. So then what we will do, we'll use the Nusselt's number for the fully
Heat
developed
to
flow.
Polter.
Did yeah, correct. So Dittus-Bolter is for turbulent flow, but I am not saying whether it is turbulent or laminar.
Yes,
Based
yes.
on that,
Yes, ma'am.
you will use the corresponding equation.
Okay, ma'am.
Okay, so from Nusselt's number, then you will get H, that is the heat transfer coefficient, and from heat transfer coefficient, you will get what? You will get just 1 second. Yeah, from heat transfer coefficient for constant surface temperature, for yeah, for constant heat flux, there is one equation that's given in the class, right? Have you got that equation?
Um,
Surface temperature my is equal to mean fluid temperature plus Qs dot upon H. Okay, let me provide you this equation so it will be easier for you. Surface temperature, this is for constant heat flux. We can use this equation. I have already told you, no, one is constant heat flux, another is constant surface temperature.
yes,
These
ma'am.
are the two phenomena. Sir, I have already taught you in the class, I think. So this is the basics. These are one of the basic for flow inside a pipe. So for constant heat flux, we will use this equation. Ts is equal to Tm plus Qs dot upon H. Right? So heat transfer coefficient we have calculated now, and Qs also we have calculated, right? This constant heat flux. This
Yes, ma'am.
constant heat flux, as I've already said, you heat transfer rate upon A. So this we have calculated, and from that, if we know the mean temperature, is the mean temperature given? Yeah, mean temperature is given as 65, right? The water is to be heated from 15 to 65. So mean temperature is given as 65. Understood?
Yes, ma'am. Yes, ma'am.
Yeah. So mean temperature is already given as 65 degrees Celsius. So from that surface temperature can be found. Any doubt?
No.
So first what we will do, again let me recapitulate. First we will find out what? We will find out the Q, the
Mass
heat
flow rate.
transfer. Yeah, mass flow rate, yeah. That you will find out, but for like what, where you will use that basically. First, let me clear out the steps. First, we
Okay.
have to find out Q, that is the heat transfer. How much heat transfer, rate of heat transfer is there. For that, we don't know H. We don't know anything here, right? We don't know H, so we can't give the formula of H delta T. We cannot use that. So we have to use Cp is there. So and volumetric flow rate is also given. So M, like mass flow rate we can find out. So if we find out mass flow rate, MCP delta T we can easily apply. Delta T also we know, right? So MCP
Yes,
delta T
ma'am.
will apply, and Q we will find out. So once Q will find out, first part of the problem is solved. That is the heat that is transferred from the heater to the surface. Now the second part of problem is from the surface to the fluid, the bulk fluid. Now then comes the heat, like we want heat flux. So heat flux obviously upon area, that you calculate how to do, right? Now for that, for finding the mean temperature, first thing that we need to understand, for any flow inside a pipe, when there will be flow inside a pipe, we have to find out the entry length first. And for finding out the entry length, or whether it is a fully developed flow or not, we need to find out entry length. And for entry length, we need to first find out the Reynolds number, right? And so first we'll calculate the Reynolds number. Hello, hello, am I
Yes,
audible?
ma'am. Actually, my net was
Acha,
a little fluctuating. So.
no problem. So first we will find out the Reynolds number for understanding whether it is fully developed flow or not. Because for if it is not fully developed flow, then also there are some equations that are available. You can get that in the book, right? And even if it will be applied, like it will be given in the question itself, right? So first we have to find out the entry length, and if we find out the entry length, we can understand whether it is fully developed flow or not. It is fully developed flow, then we can use some Nusselt's number equation, and if it is not, then we can use some equation, right? So based on that Nusselt's number equation, we can directly find out the heat transfer coefficient, and from heat transfer coefficient, we can use this, the equation that is given here, for constant heat flux. So from there, mean temperature we know that 65 degrees Celsius, so we can find out the surface temperature.
Yes, ma'am.
Understood?
Yes, ma'am.
Okay, then this I'll give as homework. We'll solve it in the next class.
Okay.
Okay, it's way too late. Go have your dinner.
Yes,
I
ma'am.
hope you enjoyed today's class. Okay,
Yes, ma'am.
talk to you next week. Bye bye.
Thank you, ma'am. Bye.